This is amazing. So
if you think this is well, then you've got a lot to do. This is the small one. Do you want to go and see if we can see the big one?
Yeah, let's do it.
Let's go through here. Maybe we can go down there as well. Yeah, that's the big shot.
It's not small, is it?
No.
That is huge.
Yeah, it's not small.
Hello and welcome to Crowd Science from the BBC World Service. I'm Anand Jagatia, and on this week's programme we are going big and very, very small. That's because we've come to one of the largest science experiments on Earth, the Large Hadron Collider at CERN, which is the European Organisation for Nuclear Research, or Conseil Européen pour la Recherche Nucléaire, if you'll excuse my French. Here, in an enormous circular concrete tunnel under the border between France and Switzerland, thousands of scientists, engineers and technicians are smashing tiny particles together at close to the speed of light, trying to recreate conditions from just after the Big Bang to find out what our universe itself is made of. In fact, why it's here at all. This is huge stuff. And the reason we're here, like every week, is because of a question from one of you. Here's Crowd Science listener Doug from Canada.
Hi, Crowd Science. I'm Doug Baker from Gibsons, near Vancouver in Canada. My question for today's program is there a limit to how much physicists at CERN can discover? Are there foreseeable limits to knowledge?
This is a fascinating question, Doug, and it's a bit of a deep one, I think. So what's the reasoning behind it?
I think I heard a cosmologist some years ago talking. There was some discovery, I don't know what it was, but the cosmologist, if I'm right on this, said that he could see the limits, the foreseeable kind of a horizon. And I was thinking, well, of course, there's always things they keep discovering. There's always the unknown to be explored, and they keep looking and they keep discovering things. But one of the interesting concepts, I think, or the problems with knowledge is that every time science discovers something, very often it offers about 4 more questions. You know, when they found a particle, they realized, oh, there must be another particle affecting it, so we better go find that. And if that's correct, it tells us that the more knowledge we get, the more we realize is unknown.
Thanks, Doug. This really is a fantastic question. Will we ever know what the universe is made of? Is there a limit to what physicists can discover? Well, if there's anywhere they can figure this stuff out, you'd think that the Large Hadron Collider at CERN would be it. The LHC is the biggest machine that human beings have ever created, and to scientists, this place is revered. Physicists from all over the world come here and use the collider to ask fundamental questions about our universe.
Bonjour, excuse me, parlez-vous anglais? Do you speak English?
Producer Jen met some of them in the CERN cafeteria, which is full of scientists of all nationalities, and does an excellent lunch, by the way.
I'm Valentina, I'm an Italian PhD student and work at CERN in the ATLAS experiment.
I'm Haas Abu-Zeid, I'm a Canadian, but I'm working for a Danish university.
This is Keisuke Yoshihara. I'm from Japan, working in the ATLAS experiment now.
So I'm Kati. I'm from Finland. I've been here almost 30 years.
Hi, and I'm Zunia. I work with Kati. I'm from Germany and I've been here for 9 years now.
So how many people work at CERN? We asked our guide, European Communications Officer Stephanie Hills.
Well, that's a really interesting question. So if you want to ask me how many people work for CERN, that's about 2,500. And in terms of the number of users who come here to work on the experiments, that's about 13,000.
Time to go and see a particle collider. The site is so big that we have to drive 20 minutes to see our first experiment and cross a country border on the way.
So Steph, are we in France now? Have we crossed over?
Yep, we just crossed over the border. In fact, most of the LHC is in France. It's just the main CERN sites in Switzerland and a few of the smaller experiments.
Well, I've just got a text on my phone saying welcome to France, so yeah, I can confirm.
I suspect you're going to get quite a few of those today. Welcome to Switzerland, welcome to France, oh, welcome back to France.
Yeah.
From the surface, all you can see is bright green fields and peaceful Swiss farmland, framed by the Jura Mountains and the Alps. Only the odd sign which says LHC Access Point gives a clue to the truly colossal scientific enterprise under your feet. The LHC is a giant ring housed in an underground tunnel 27 kilometres around. There are 4 main experiments dotted at different points around the ring, so it can take a while to get between them. Whilst we're on our way, let's come back to Doug's question. He wants to know if there's a limit to what physicists can discover about what makes up the universe. Let's start with what they already know. What makes up all of the stuff around us, the air, the ground, trees, people, sandwiches, has fascinated scientists for thousands of years. If we had some kind of magical camera that could zoom in to incredibly small levels, we'd first see that everything, all stuff or matter, is made of atoms, tiny building blocks named by the ancient Greeks. But we've since learned that even atoms are made of yet smaller things. Electrons, which you've probably heard of, they give us electricity, as well as protons and neutrons. As far as we know, electrons are only made of themselves. There's nothing tinier inside them. But zooming into protons and neutrons, you'd see that they are actually made of even smaller particles. Now, if this Russian doll situation of particles inside particles is making your head spin, don't worry, it is confusing. Especially when you start to hear all of the names physicists have given to these particles. Quarks, muons, gluons, I think taus are probably my favourite. In total, there are 12 particles that we know of which make up all the matter in the universe. And these particles are held together by fundamental forces, which are themselves carried by particles. Hang in there, we're nearly done. All of these particles exist in the universe, but some of them are much rarer than others. These rare particles only exist at very high energies, like just after the Big Bang, or when a star blows up in a supernova, or in a particle collider like the LHC. And that's essentially what physicists at the LHC are trying to do, create some of these rarer particles that we just can't see elsewhere. And it was in 2012 that they did just that, when they told the world they'd finally found the Higgs boson, a particle that gives all the others their substance or mass. It was proposed to exist way back in the 1960s, and it's named after physicist Peter Higgs, who was here at CERN on the day they announced its discovery.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
Finding the Higgs was a really big deal, as you can hear, because along with the 12 particles we mentioned earlier, it completes the best picture that physicists currently have for the particles and forces that make up our universe, called the Standard Model. Although that extraordinary discovery feels like the end to the story, it really wasn't.
Imagine Columbus is trying to find a new route to India by going west instead of by going east. And he reaches land, and he thinks, I've discovered the West Indies, I found this new route. That's kind of where we were back in 2012. We'd found something, we thought it was the Higgs boson. We're now pretty sure that's exactly what we've discovered, but we know more about it than we ever dreamed we would know, actually.
This is applied physicist Dr. David Barney, whose main role is to design, build and operate particle detectors. We meet him standing on top of his experiment, CMS, or the Compact Muon Solenoid, which in reality is anything but compact. It's massive.
It's one of the biggest, it's definitely the best particle
you
detector.
Would say that,
I'm slightly biased, yeah. It's roughly 100 metres directly below our feet now, and we're standing at what we call the big access shaft that leads down to where the detector is in its cavern underground.
Well, let's talk a bit about the detector itself. So beneath our feet, there's this huge ring, which is the Large Hadron Collider, which kind of crosses 2 countries. Can you explain to us broadly the structure of this massive scientific experiment?
If I were to explain what we do at CERN in just one phrase, what I would say is we smash things together and we see what happens. And the job of the LHC is to smash things together. Smash very tiny things together, smashes protons together at nearly the speed of light. And then from those tiny collisions, we can try and understand things about the universe. But we can only understand them if we see what happens. And to see is maybe a slight misnomer. We don't really see. We can figure out what happened in those collisions using things that you could imagine as digital cameras, but not small digital cameras. The CMS example is 14,000 tons, 20 metres long, 15 metres high, 15 metres wide. We take photographs 40 million times every second when we're operating.
You just can't even get your head around those kind of numbers.
I remember working out a few years back, it was like everybody in the world taking a digital photograph once every hour or so. The amount of data that would produce, that's what we produce, but every second. So we do that here at CMS. On the opposite side of the ring, let's say we're at 12 o'clock. At 6 o'clock, there's another detector called Atlas that does the same sort of thing. And then next to that, at 5 o'clock and 7 o'clock, are two other experiments called LHCb and ALICE that also do similar things. Now, CMS and Atlas are what we call general purpose. They'll look at any type of collision to find what might be out there. LHCb and ALICE are much more specialised. They look for very specific occurrences in these collisions.
Well, let's talk a bit more about these collisions then. So you said that at CERN you smash things together almost at the speed of light and then photograph, in quote marks, photograph what happens. So these things that you're sending at fast speeds round towards each other, they're protons.
Majority of the time, what we accelerate in the LHC are indeed protons. What we're looking for are not necessarily things that are smaller than the proton. We can be looking for things that are much, much bigger than the proton by colliding protons together, which is somehow a perverse thought.
So people might think that what you're doing is you're smashing these protons together and you're kind of trying to break them open somehow and see what's inside, but that's not what's happening.
Right. I mean, in the early days of CERN and particle physics, that was exactly what we were doing. So if you wanted to know what your smartphone was made of, what would you do? You probably
put it in a blender.
Yeah, you put it in a blender, or you smash a couple of them together in our sort of parlance. So what you'd ideally do is just smash them together and you get the smaller bits and you figure out what it's made of. The interesting thing occurred when what we found in some of the collisions a long time ago was not things that were inside the atoms or the protons that we were colliding. They were something else, and they were actually more massive. They were bigger than what we started with, which is incredibly weird to think about. It's almost like alchemy or magic. You're colliding something together, you're getting something bigger out. Imagine, if you like, colliding a couple of Lego helicopters, which is something I do for fun with visitors. You collide a couple of Lego helicopters and what you create is a couple of dinosaurs. We don't really create dinosaurs, but what we do create is things that are bigger than we started with, not smaller, and something that used to exist but doesn't anymore. And these things used to exist. The things we're finding now used to exist freely in the very, very early universe, fraction of a second after the Big Bang. So, yeah, it's a bit like magic, but time machine magic.
And so, essentially, what you're trying to recreate in these collisions are the conditions, the energies that we found much earlier back in time, a fraction of a second after the Big Bang.
Right, essentially what we're trying to do in the end is understand the universe.
You're listening to Crowd Science from the BBC World Service, and today we've come to the Large Hadron Collider in France and Switzerland to answer Doug's question. Is there a limit to what physicists at CERN can discover? And will we ever know what the universe is made of? Physicists have made a pretty good start at answering that second one, but there is still a lot we don't know. Back to physicist Dave Barney inside the LHC.
Well, I could say this railing is made of metal, this floor is made of concrete. This microphone is made of this fluffy substance that's there with some electronics and some metal and some plastics underneath it. Let's break those down, we'll eventually get to atoms. Break those down, we get to protons, electrons and neutrons. Break those down even further, well, we can't go any further, at least as yet we haven't gone any further with electrons, but with the protons and neutrons, we've found that they're made of the same thing, called quarks, called up and down quarks. And it turns out that everything in here, everything, if we look out at the stars and the galaxies, breaks down to 3 particles, just 3. It's like 3 basic building bricks. Up quark, down quark, electron. Everything's made of that. Sounds like a really simple picture of the universe. Unfortunately, or maybe fortunately, it's not that simple. If we look at how galaxies behave, there's not just these up quarks, down quarks and electrons. There's something else there that we can't see. We imaginatively call it dark matter. And that explains why galaxies move in the way that they do. There's something massive out there, and not just out there, but here as well, going through us all the time, that we can't detect, this dark matter. And it's not just a tiny fraction. In fact, it's the big fraction. Of all the matter that's out there in the universe, about 4/5 of it is dark matter, and only 1/5 is these up quarks, down quarks and electrons. So we understand nothing about the universe.
We've only been studying about 20% of everything.
Oh, much worse than that. So in fact, the matter is only one part of the story. There's also something called dark energy. You know, it's like this hidden force that's out there as well, that is about 3 times as much as the matter there. So we're only really been studying 5% of the universe.
So, particle physicists have still got their work cut out for them. Here at CERN, they're also looking into something which Dave mentioned. What's the deal with antimatter? This research is happening at another experiment on the ring a few kilometres away called LHCb. And this time, we've been granted access to actually head underground into the LHC itself. This is normally a highly restricted site, so first we have to get our security clearance.
Please center your eyes. Thank you. Your identity has been verified.
Retinas scanned, access tokens issued, we are off to the LHCb experiment, where we put on hard hats and walk to security. But first, Jen has to do something that makes all radio producers nervous, and leave her beloved microphone behind.
Yeah, leave your equipment there.
Oh, I see. Okay.
You're going to put your bags down?
Yeah.
Because otherwise the machine thinks that you've got another person with you.
Oh, I see. Right. So we just walk through and pick out the other side?
Now we just need to use our newly verified eyeballs to get through the security system. Turns out the security systems at particle colliders are a nightmare, and I thought airports were bad. Eventually, we get through, Jen is reunited with her recording equipment,
Hello.
and we start our descent underground.
So are we going all the way down to the bottom?
Yes,
100 metres.
103 meters underground.
This is quite a fast lift.
Yes.
It will stop at the bottom, right?
It's a one stop only.
Wow. This is like bigger than a cathedral. You could fit a cathedral comfortably inside this cavern. There are workers you can hear in the background, but there are just scaffolding and cranes and little bits of electronics poking out and cables and wires just everywhere. It looks like a massive version of the kind of Lego and Meccano contraptions I used to build when I was a kid. I'm just kind of speechless, really. This is the biggest experiment I've ever seen. Dave told me earlier that CMS was the best one, but now I'm not so sure. What does our LHCb researcher think?
Well, of course, we're going to disagree with that. Well, you know, they helped find the Higgs, which was a really important thing, but I think it was us who made most of the better discoveries after that time. So
Okay. And so you
it's our era now.
Yes, your era, the era of beauty. The B in LHCb stands for beauty. Dr. Tara Nanut explains why.
So essentially, beauty and charm are just what we call two of these particles that make matter, so they're quarks. It makes physics much more interesting if we talk about strange particles and charm particles and beauty particles than, B, C, quarks.
The LHCb experiment is similar to CMS in that they're both smashing particles together to see what they can learn from the collisions. So how is this one different?
What we do here is more precision physics, so we instead measure processes that we mostly know they exist, but with really, really high precision, and we try to find things that would also indicate that there is something new. So you can maybe compare these two detectors. DMS would be like maybe getting a really, really large telescope and searching the wide ocean for seeing a ship. What we do here is instead we're going to measure all the waves, and from the direction of the waves we're going to try to infer is there a ship and how big it is and where it is.
Okay.
So that's a different approach. They're just going to build a really big-ass telescope and search for it directly, and we're going to instead measure really delicately all the other parameters and try to see indirectly whether there was a ship and where it was.
What kind of questions are you looking at here in your research?
So one of the main missions of LHCb is researching CP violation. So this sounds again very scientifically confusing, but essentially, it's the same philosophical question as if we put it, why are we here? The CP is the symmetry between matter and antimatter, and violation implies that this symmetry is broken. And we know that this symmetry is broken because we know that when there was the Big Bang and the universe was created, there were equal amounts of particles and antiparticles, matter and antimatter. But of course, everything we know today, the entire universe, everything is just matter. So where did all the antimatter go? And what we do here is we try to measure this dominance of matter over antimatter that would help us explain how is it even possible that the universe came to be the way it is.
How is antimatter different from matter? So me and you are all made of matter, right? But there is this other stuff out there in the universe called antimatter.
Yeah, exactly. The point of antimatter, it's supposed to be exactly the same as matter, only things we call quantum numbers would be completely reversed. For a very quick comparison, you can imagine it. Matter is you and antimatter is you in the mirror. So if you raise your right hand, antimatter you is going to raise its left hand.
If it was possible for me to meet my mirror self and shake his hand, what would happen?
Oh, a big, big, big explosion. You don't want to do that. That's what matter and antimatter do. When they collide, they will annihilate each other.
Is that why we're so confused about why there is so much matter in the universe today? Because if there were equal amounts of matter and antimatter at the Big Bang, then they should have all annihilated and we would have no matter. But we do
exactly. Everything would be obliterated. The universe would be just a big, empty space. Well, it's still pretty big and pretty empty, but luckily we do have some matter here and there, like, stars and planets and us.
So good advice from a physicist there. If you ever do meet your antimatter equivalent, don't shake hands. That said, at LHCb they do create tiny amounts of antimatter in their particle collisions so they can study how it behaves.
We create it here. Unfortunately, it's not going to be long-lived.
Do you think that physicists will find the answers to explaining what the universe is and answering these big questions? So the Standard Model tells us a lot of things, but there are a lot of things it can't tell us. It doesn't work.
Yeah, exactly.
So do you think we will?
I most certainly think we definitely will eventually find an answer to all of it. Just the question is where and how big of a collider we're going to have to build before we find that.
That is the $1 million question. Actually, it's a $20 billion question. CERN have proposed a new circular collider 100 kilometres long to replace the current 27 kilometre Large Hadron Collider. So maybe the limit to what particle physicists can discover might be cost. Or perhaps they might have to try something completely different.
It's more on the centimetre scale.
CERN is 27 kilometres?
Yeah.
And this is on the level of a centimetre?
Yeah, at the moment in a centimetre we're reaching much lower energies, but we could reach the same energies as a few kilometre accelerator in under a metre.
Dr. Charlotte Palmer is a research associate at the University of Oxford. We met at the Central Laser Facility at the Rutherford Appleton Laboratory, which is just outside Oxford in the UK. Lots of signs everywhere saying, danger, lasers!
Yeah. At the moment, there is no laser hazard on,
Okay,
so we're perfectly safe and we can go inside, but we have to get kitted up to make sure we stay clean.
Cool, okay.
And the lab stays clean as well.
Yeah, most importantly. The 2-beam Gemini laser here is a particularly intense one. In fact, it's kept inside a bunker with concrete walls 1.5 meters thick and a lead-lined door for good measure. Inside the bunker is a blue vacuum chamber about the size of a fridge, and inside that, Charlotte has to point out the particle accelerator.
You can see this box that's maybe 15 centimetres long.
Oh, what, the thing going across
This
that?
little grey...
with the tube coming out of it.
So in California at the Berkeley lab, they've used 20 centimetre long to get up to the highest energies that have so far been achieved with this technology.
And how high are the energies that you can get to? Like, compared to the energies that you can accelerate particles to at somewhere like the Large Hadron Collider, how does it work here?
So we're still at much, much lower levels than the Large Hadron Collider. And another big difference is that they're using proton beams, whereas this is primarily electron beams from Wakefields. We can reach close to 8 GeV, which probably doesn't mean much to people, but in comparison with other technologies, so there's a very large accelerator that's just been built in Hamburg that gets up to 17 GeV, and that's multiple kilometres long.
Just to put that in context, 8 GeV, or giga electron volts, is about 1,000 times less than the energy they can produce in collisions at the LHC. That currently holds the world record for total collision energy, which is 13 tera electron volts. So the LHC is still in a league of its own. But seriously, after having been there and seen for myself just how jaw-droppingly enormous it is, the fact that this tiny collider can come anywhere close is incredibly impressive. So how does it work? Charlotte explains that it uses something called plasma Wakefield acceleration.
Plasma is the fourth state of matter after solids, liquids and gases, and it's basically composed of taking an atom and splitting it up further into its positive and negative parts. So the protons and nucleons that are in the nucleus and the electrons.
So that's the plasma side of things.
Yeah.
And it's this kind of cloud of charged gas.
Yeah, like a sea of charged gas.
Then what happens once you've generated that?
If you put a laser pulse or a particle beam through that, then the charged particles inside the plasma move in the same way as like water moving around a boat. So quite often people use this analogy of a motorboat moving through water, and then you get a wave behind it called a Wakefield. And so then we've got a wave that's moving through the plasma, and effectively electrons inside this background plasma can sort of sit on that wave like a surfer and then gain energy in this plasma wave.
I can definitely see the benefits of having a smaller, presumably less expensive setup for particle acceleration. Is it less expensive?
Yeah, so the lasers are still research machines, so they're not cheap, but lasers have come a very long way since their development in the 60s. As the technology becomes more widespread, it gets cheaper.
We've been talking a bit about funding, so CERN have put in this proposal together to build the Future Circular Collider, which is going to be about 100 kilometres long. Do you think that we should be funding big experiments like that, or developing smaller projects like this one?
That is quite difficult. So obviously I'm very biased because this is my research. And I mean, I would love to see more money available for this research. But I think one of the things to remember is the CERN accelerator is based on proven technology. So they would just be building a bigger version of something that works already, whereas we have a lot of kinks to work out.
So plasma Wakefield accelerators still have a way to go, but interest in them is growing, and they could provide physicists another option. But there's a bigger question here. However it's done, it seems like approaching the limits of particle physics really isn't cheap. So, is it worth it? Should we be spending the money on research to fix other problems, like climate change? Back at the LHC, I put the question to Dave.
So, I would never say that we should spend money on this instead of spending money on climate change. But we should definitely do this, because this is what sets us apart, in my opinion, from every other creature on Earth, our desire to understand. And where that will lead us is not clear to me at all. I don't know what will come out of this. 30 years ago, things like the World Wide Web wouldn't have been dreamed of. That came out of CERN, just from a need to communicate better. Things like cancer treatments and cancer diagnostics, that technology comes directly from CERN and places like CERN. So things are coming out of this that we can't predict. CERN has an operating budget of around 1 billion Swiss francs per year. To you and I, of course, that's a huge amount of money. But when you look at the member states who fund CERN, what that's equivalent to in terms of their taxes, it's a couple of cups of coffee per taxpayer per year. It's about the same as an average university. And what we get from it could be completely game-changing.
I wonder what listener Doug makes of that. Does he think CERN should build an even bigger collider?
Absolutely, beyond question. And I hope my country is contributing significantly to it, because I think there's value in knowledge for knowledge's sake. I think ultimately society progresses by that. But I also think that inevitably the so-called pure knowledge yields unforeseen benefits. Inevitably. I think we live with those in our day-to-day lives every single day.
So Doug asked, is there a limit to what physicists at CERN can discover? Well, in a way, it seems like CERN has hit a limit with what they can discover using their current setup, which is why they want to go even bigger. And given the financial, political and scientific factors that will be involved, perhaps the limits will just be boring practical ones. But then again, given what they've managed to build and achieve so far, maybe those things won't stand in their way. Perhaps physicists will be able to reach the higher collision energies with completely different technology, like the plasma Wakefield accelerators we saw at Oxford. And given that CERN is also researching plasma Wakefields, maybe they'll all end up working together anyway. What about on a more fundamental level? Is there truly a limit to the kinds of things particle physicists can and will discover? We asked the actual particle physicists that we've met so far. Last word to Charlotte Palmer, Tara Nanut and Dave Barney to see what they think.
People have in the past thought that they've understood everything, and it's always turned out that we're wrong in some way or there's something extra to learn. So I think there'll be like many more exciting things to discover in the future.
Okay, so there's not a limit on the things that we can discover, but do you think there's a limit on the things that we will discover?
Well, it just depends on how persistent people are, I think. And people can be pretty persistent.
We could say we are limited by the energy of what we can reach. Even the Earth is a limited resource, so at some point we are going to be limited in energy. There is only so big of a collider that we could ever build. So unfortunately we are a little bit limited by the physics that our Mother Earth offers us, so to say.
Is there a limit to our imagination? And is there a limit to the imagination of the human race? What we're doing is not complex in a way. Smash things together, see what happens. To be able to do that really pushes the boundaries of technology. The humble physicists like myself, we keep pushing the engineers all the time, and they keep coming up with answers. And by coming up with those answers, they're also pushing the limits of what can happen in other fields. So I don't think there is any limit. The limit may become financial in the end, but there's no real limit to our imagination, so then there's no limit to what we can do if we really put our minds to it.
So do you think that one day we will have a full, complete picture of what the universe is made of and, you know, all the forces, not just a few of them?
I think that we will. I'll be kind of sad when that day happens. It probably will not be in my lifetime. It's like saying, you know, we've explored all of this now. What do we do next?
That's it for this edition of Crowd Science from the BBC World Service. Today's question was from me, Douglas, in Canada. The presenter was Anand Jagatia, and the producer was Jen Winty. If you have a question about life, Earth, or the universe, please email it to crowdscience@bbc.co.uk. Thanks for listening. Bye.